under the supervision of Enrique, as I understand.
Mm-hmm.
He is a FAPESP scholar, and the title of his talk, you can see it on your screen. It's Instantons on asymptotically locally conical G2-metrics. So thanks for accepting our invitation, Jakob, and the word is yours.
Thank you. Thank you for inviting me to speak. I have just arrived at Unicamp from the UK as a Bridges associate, I guess. So I'm looking forward to getting to know the mathematical community here in South America. So it's good that I've been allowed to advertise myself and meet all of you. So what I'm going to be talking about today, at the very basic level, is just the solution space to a time-dependent ODE system, which comes from the Yang-Mills instanton equation on what's called the cohomogeneity 1 G2 manifold, and the gauge group of this Yang-Mills action is SU2. Very specifically, the cohomogeneity 1 G2 manifold I'm going to be talking about is called the B7 family of G2 metrics on a manifold with topology S3 times R4. And to sort of explain some of the things about this solution space that we're going to obtain, I'm going to tell you a bit about asymptotically locally conical geometry, which is displayed by this B7 family, and also asymptotically conical limits. So there will be a limit of this B7 family which will have different asymptotic geometry. So I'm going to say a bit about that, and we'll see it very explicitly. And then I'm going to talk a bit about the ODE analysis. Not all of it's completely standard, that you use to find the solution space. The solution space will turn out to be non-compact. And to understand compactifications of this solution space, I'm going to talk a bit about instantons. So these are Yang-Mills instantons, or anti-self-dual connections in 4 dimensions on a space called Taub-NUT, which is a Ricci flat metric on R4, and describe the solution space there, and to relate that to what's called ALC or ALF, vibrations, which I haven't seen studied in the literature very much, but turn up in a very specific way here. Just a word again, if people missed the discussion we were having just before the seminar started, there's this funny thing about ALF and ALC. ALF just is the ALC is just and ALF are basically the same thing. It's just people call ALF things, ALC things ALF in 4 dimensions specifically. There's some other stuff, but for purposes of this, ALC and ALF are the same. And ALF stands for asymptotically locally flat, for anyone interested. Right. Okay. Sorry, so before I go on, so that's what we're going to see today. Are there any questions before I move on to some motivation about these things? No? Okay, if not. This is, well, building on previous partial results by Jason Lotte and Gonzalo Oliveira, I think in 2018, I believe it is, who described some of this space that we're going to, but wasn't able to understand how it varies in the family, wasn't able to understand limits, and only described some sort of open set in this modular space, in this solution space. And this whole idea of introducing ALF vibrations is sort of ripe for analysis, partly because there's been a recent work classifying instantons on these ALF spaces called multi-Taub-NUT, which was generalizations of Taub-NUT metrics, by Cherkis and some others. So understanding how they lift now is sort of a more viable thing. Right, and I should say this project is based on joint work with Matt Turner, formerly of University of Bath. And also I should thank and mention Lorenzo Foscolo and Calum for our joint. I mean, some of this work, especially the stuff that's happening on Taub-NUT, is based on our discussions. So I should also include their names there. Right. Okay. So that's. I mean, it's a motivated problem to construct these Yang-Mills-Instantons on these types of geometries. I should say there's lots of examples of these ALC metrics, and understanding what happens to their instantons is sort of an unknown thing. Okay, so let's actually talk about the geometry. If I have four functions, positive functions, A1, A3, B1, B3, that satisfy this ODE system, which, right, it's the solutions exist for all time. Then I can construct an SU2 squared invariant metric with Riemannian holonomy group G2, exactly G2, on the interval times S3 times S3, where I think of this as S3 times S3 as two copies of SU2. And I fix a basis of left invariant one forms, EI and EI prime, to denote the different copies of S3. Then I can write a metric on this space so I'm thinking of T here as parameterizing this interval, and then I set this AI multiplying these linear combinations of the left invariant one forms here, and the BIs multiplying this linear combination. Okay, and there's some, actually, what I've written down in this equation one is even more general. In this specific case, there's actually an additional U1 symmetry where I think about acting on the right by the vector field generated by E3, and I rotate the space spanned by the tangent space spanned by E1 and E2. So actually, in terms of the functions, it just means A1 is equal to A2 and B1 is equal to B2 in this formula. Right, so if I have this ODE system, which turns out just to be the equations for a torsion-free G2 structure for this form of the metric, then actually I get a metric with Riemannian holonomy G2. Okay, and I can think of this as sort of writing down a metric on S3 times R4 in polar coordinates by thinking about extending these functions to t equals 0, and extending it to the copy of S3 at t equals 0. And turns out I can write down these solutions in a two-parameter family to these ODEs that extend smoothly to define a complete metric on S3 times R4. So I've called the two parameters R0 and L. One of these parameters actually is sort of doesn't really is just rescaling the metric, right? I can just think about an overall rescaling the metric. It's not really going to change the geometry. It's just a constant. So I can think, let's fix that. So now there's this one parameter family, so for fixed overall scale of metrics, parameters by L, and this controls the asymptotic behavior when I fix this scale. In terms of the functions, I have this behavior of these functions as t goes to infinity, where A1, B1, B3 are all linear, and then A3 is this converges to this fixed constant. What does that mean in terms of the metric? The metric behaves at infinity as a product of a conical metric, cone metric of one dimension less, dt squared times t squared g5, plus circle 5 actually over this 5-dimensional, this 6-dimensional cone of fixed length L squared, or fixed length L, sorry. Okay, and actually we can say a bit more. I mean, this is a G2 manifold, and actually we would expect this cone to be Ricci flat, and indeed it is. In fact, it's this conical metric is the Calabi-Yau cone metric on what's called the conifold. So you can think of that as the vanishing of this quadratic polynomial in C4. The zero locus of this quadratic polynomial. Right, and the metric on this thing was constructed by Candelas and Della Ossa, and it is a cone over, so in terms of SU2 squared, it's the metric cone over homogeneous Sasaki-Einstein metric on SU2 squared mod out the diagonal copy of U1, acting as 1 in both factors. Right, and then you can see that this is sort of how this is a circle vibration over that guy. It's just the vibration that's given by SU2 squared. The total space is SU2 squared. Right. Right, so that was the form of the metric. And this is sort of an example of what's called asymptotically locally conical geometry, by which I mean the tangent cone at infinity of this metric is 1 dimension less than the dimension of the metric itself. Right, so if I rescale at infinity, I'm going to get something that collapses down to something 6-dimensional at the cone. And the volumes of like a geodesic ball in my manifold as t goes very large is 1 dimension less than the maximum possible volume growth, which would be t to the 7-dimensional metric. Right. So the analogy for this type of geometry, how these things were first written about, is for 4-dimensional metrics, which have the name asymptotically locally flat, ALF. So the prototypical example of this is the Taub-NUT metric on R4. There's a Ricci flat, in fact, hypercalometric on R4, not the standard one. It's given by the following expression. And you can see it's completely analogous. It's like a circle vibration over a cone of 1 dimension less, and the volume growth is all r to the r cubed, simply because you recognize that the vibration here is over, the cone over S2, which is just R3. I haven't written it in geodesic. I haven't parameterized this coordinate r by arc length, but it's the same behavior. Okay, so it's completely analogous thing, and you can actually try and generalize this concept to higher dimensions, and there are these examples, these ALC examples. There's actually infinitely many examples now thanks to constructions of Foscolo, Haskins, Nordstrom on asymptotically conical Calabi-Yau metrics. You can produce families of arbitrarily high dimension from their construction. So it's not an empty, it's not just a B7 family, it's many metrics like this. And we're going to see the Taub-NUT metric appear again later, actually. Okay, so that was the background, quick introduction to the background geometry. Is there any questions about any of that? If not, so now let's actually get into the problem that we're trying to solve, which is the G2-instanton equation. So if I'm given two functions, if they solve this ODE system, so now it's a time dependent, it depends explicitly on, it's not just a function of F1 and F3, it's a function of F1, F3, and these metric coefficients. So it depends on time explicitly. We can construct ansatz for an SU2 squared invariant Yang-Mills instanton, so it satisfies that the derivative with respect, the codifferential with respect to this connection of the codifferential with respect to this connection of the curvature of that connection is 0 on the interval. Yep. Hello?
Can you just rewind a bit? I think I missed some of what you said. Don't know if others did. I think there was a little cut.
Oh, where did I?
Yeah, no. Just on the last slide, just when you start talking about Yang-Mills, about instantons.
Ah, okay, sorry. So I'll repeat what I said about these. Given these two functions, you can construct an SU2 squared invariant Yang-Mills instanton on the interval times S3 times S3, where Yang-Mills instanton is a solution to taking, it's this thing here. I take the codifferential with respect to the connection of the curvature of this connection, and it's 0. Well, it means to be Yang-Mills, and it's actually of the special form. It's actually a G2-instanton, which is a first order condition, a stronger first order condition. If you know about what that is.
Yeah. So what's the bundle? What's the bundle?
This is it will be clear from what I'm about to say.
Okay, and what's E prime?
So E prime is it's the same as what I said before for this. It's the basis of left invariant 1 forms on the second copy of S3.
Oh, I see. Okay. Right.
So I can write down a Lie algebra valued 1 form on the space of the trivial bundle on R4 on S3 times S3 times the interval, which is just given by I take the dual of one of these copies of S3, the vector field that's dual to one of these copies of S3. I mean, it's just a convention, and then I tensor it with the 1 form on the S3 that's diagonally embedded in S3 times S3. And then I multiply by some of these functions, EI. So yeah. And there's something slightly wrong here. It should say, no, that formula is correct. So the bundle is in fact trivial. In fact, the SU2 action here is also trivial on the fiber. It just acts on the base. Right. And I can think about, in the same way I can think about writing down metric and polar coordinates, I can also think about writing down the bundle in a similar way. So I'm going to get some boundary conditions for extending this connection to the S3 at t equals 0. and that's going to give me some parameterize some family of solutions near this S3. And what you want to know is, okay, now if I can parameterize my solutions just near, so from small t, which of these solutions lives for all time, and what's the behavior of those solutions? Okay, and that is in fact the theorem. So there's a two-parameter family of solutions which close smoothly on this S3. So they're parameterized by these two constants, f1 bar and f3 bar. And if I look at what solutions exist for all time, I have a region which is, so I have a line which is just setting f1 bar to be 0, which actually has the effect, if we look at the ODE system, is I just kill off f1. And what that means geometrically is that I've been thinking about this being a Yang-Mills instanton on the copy of U1 that sits inside SU2. So in fact, what if I set F1 to be 0, I'm actually getting an abelian instanton, which we sort of expect to be there because I could take the killing field, which is generated by this additional U1 action that I was talking about before that rotates the copy of E1 and E2. I take that killing field. That's in fact I can just add some constant on top of it to this killing field, and that gives me an instanton. So I'm always expecting that to be there. Now I then have a region that is does lead to complete solutions, and the boundary of this region corresponds to solutions that have this constant, so that have F3 at infinity converging to 1. And I'll explain as I explain how you prove this, I'll interpret what all of these things mean. And I should say that the contribution of Lotte and Oliveira for some fixed L0, which is some value of this L where you can actually solve the ODEs for the G2 metric explicitly, so you have explicit metric. They find this green region here of complete solutions. And then the contribution of myself and Matt is, or really just Matt, is that you can do this for L near this explicit solution, this L0. And in fact, conjecturally, this picture really happens for all L. It's just that there's we can only prove some weaker version as you move away from this explicit solution. Okay, right, and the intersection is with this line of abelian solutions is just the abelian solution that corresponds to F3 going to 1, which written in terms of the initial conditions is saying that F3 bar is equal to L minus 2, L squared, 1 over L squared. Okay, and the solutions that lie outside of this region bounded by the curve, they can't be uniformly bounded for as long as they exist. They grow more than they grow. Then the norm squared of their curvature grows rather than decays. So if they exist for all time. So those aren't the solutions that we're interested in, basically. Okay, so that's the picture. Now, some ideas of the proof and what these things mean. So this F3 infinity, you can use the description of, so if I go back to it, right here, this asymptotic form of this metric is some circle vibration over the Calabi-Yau. You use this description to identify this mass, this F3 at infinity, is basically telling you about the mass of a monopole on this Calabi-Yau cone. Right, so I'm going to call this the monopole mass, this constant F3 infinity for my complete solutions. So what I do for this, how you prove this, you prove that if I have a monopole mass sufficiently large, I mean specifically greater than 1, I can actually deform my abelian solutions. So those are lying along this green line up here in a 1-parameter family for all these monopole masses greater than 1. And I'll explain that this is the step that we have the problem with. So that shows you can get this sort of this initial green region. Then we can extend the incompleteness results of Lotte and Oliveira for all L to show that both for masses lower than 1 and also if you deform sufficiently far away from the abelian solution, you actually become incomplete to get this red region. Okay, I'm on with that. Now you want to know what happens in this blue. So this blue on this blue region, which is to say you need to do 2 things. First is you need to parameterize solutions at infinity to understand what's happening there. And this is a slightly non-standard thing. We're using a theory of called irregular single initial value problems, which have the following form. So I'm thinking of X here as a vector, a vector of functions. M minus 2 and M minus 1 as matrices, linear matrices, which commute with each other. They're simultaneously diagonalizable. Basically, that's the condition we need. And then M is a honest vector of functions depending on X and time explicitly. So that turns out to be the asymptotic form of the solution, and these, you have to sort of develop a theory of this, which is based on work by Mark Haskins and Johannes Nordström, who apply it in a different setting when they're studying solitons. But anyway, so this is the sort of the analytic result that you need to prove. And then once you have that, it's sort of easier once you prove some comparison results for comparing different solutions, the values of different solutions at different times. And you can basically close up this set of initial conditions that lead to complete solutions by considering sequences that move away from these abelians, these deformed abelian solutions, to actually generate the whole solution space of invariant complete solutions. And it also tells you what happens at the boundary of that space, which is actually these do live for all time and have the behavior that I just said. Right. Right, and as I said, everything else works. The only slight problem is to get the fact that this curve exists, the behavior actually near the initial condition L1 of L squared, so up here, so this region here, you need that you can deform actually for all asymptotic monopole masses greater than 1, but we can't actually prove that for all L away from this explicit solution, sufficiently far away from this explicit solution. We can only prove some constant which goes to 1 as L goes to infinity. So it's not a complete result, but at least it says that the behavior is essentially expected at least away from this, so bounded away from this critical monopole mass, F3 infinity equals 1. Are there any questions about what I've just said? About what I'm talking about here in the analysis and the analogies that I'm making?
I think we're good.
Okay, cool. Right, so that's sort of the analysis bit. So the only sort of maybe a bit non-standard thing is this irregular single initial value problems. We're using a lot of the results of Lotte and Oliveira, but there's a nice interpretation basically of what is this moduli space near this green line. We know what the green line is. It's these killing fields, and what is near the moduli space, this solution space near the green line is deformations. Okay. So, okay, that was for some fixed L. Now, what happens when I'm taking L going to infinity? Because I know what happens to the metric. I can actually take, there's a well-defined sensible limit on compact subsets of S3 times R4, where I converge as L goes to infinity to what's called the Bryant-Salmon G2 manifold. So this, in terms of the functions, this A and B, basically everything is now linear. So the picture, the behavior of the metric is a metric cone at infinity. So I'm thinking of like unwrapping the circle fiber, essentially. The picture is here. I'm thinking about this red cone, which is approximating my geometry better and better as you go out to infinity, but near the singularity for my asymptotically conical geometry, I actually have something smooth, or maybe some topology there. Okay, in this case, it's just a copy of S3 instead of this cone singularity. Okay, and we should expect to understand the space of G2 instantons on the cone geometry in terms of the space. And indeed we do, right? Basically what's happening to this space is it's moving to the left, this curve, right?
Jacob, can I ask something?
Mm-hmm.
Are all of these G2 metrics, are they torsion free?
They're all torsion, yes. Everything here I'm talking about is torsion free.
Okay.
Yeah, sorry, I should have said that. When I say G2 manifold, I always mean torsion free. So this is the G2 instanton equation, bona fide. They are critical points. This is like, it's not some other type of ODE system, PD system. Right. So, so what we can prove is basically this space of solutions is converging to this line. So this line that bounds this boundary of the incomplete solutions up here. This is the line F1 bar equals F3 bar. The solution space, complete solutions, is basically converging to this. The boundary is converging to this line. Right, and that line where F1 is equal to F3 in this limit is actually a solution which was found on Bryant-Salmon by Clark. And it turns out in the interior of this, on this boundary, so this includes the abelian solutions, actually these now fail to be bounded anymore and blow up. So you only get this, basically what's happening is you're only getting this line in the limit. And there's also way to understand what's happening there in terms of instantons on what's called conically singular ALC G2-metrics, which are basically, that's the thing that's, there's a one parameter family of those guys which are sort of escaping off when you take this limit L going to infinity. And you're not seeing them unless you rescale. We were able to find a one parameter family of these, candidate ALC instantons on these ALC conically singular things, but we weren't able to prove anything about their long-term existence. But at least for initial conditions, that heuristic checks out. And again, when I say we proved that this curve converges, what I actually mean is outside of some small set, this curve will converge. We don't know that exactly that what happens away from, like near this point that it intersects the F1 bar equals 0 axis. Right. But we can say that the solution space does converge. Again, please interrupt me if you have any questions. But yeah, the idea of trying to prove that this problem with proving that you can deform away comes from there's a certain function which you need to have its supremum be exactly its value at infinity, but you don't know if it obtains a maximum somewhere in the interior. And in the explicit case and near the explicit case, this is basically is pretty easy, because in the explicit case, the function is just increasing. And near the explicit case, it's also going to be increasing. But in the non-explicit case, it's not true that it's always increasing. And so trying to understand what happens in the interior is very difficult, basically. But you do know that it is, as a function, the supremum is basically, so this constant CL is the supremum of this function. You know that this function is monotone in L. This is the point. Okay, so that's the idea of what is happening on this limit as you're taking L going to 0. You're actually seeing things appearing from the geometry. Okay, so that's one limit. But let's go back to thinking about, okay, I'm just fixing L, fixing my member of my B7 family. And I'm thinking about what happens, so the space of solutions is non-compact, right? I can go out taking F3 arbitrarily large and deform that solution, and that's going to give me something. So what's happening, can I understand some compactification maybe of my space of solutions as I'm going out in this region? Okay. And to understand that, I need to introduce something called ALF vibrations. So let's recall that there's these two parameters that define these functions, which are metric. And what I'm going to do is called an adiabatic limit, which means I'm going to pull back the metric by a diffeomorphism. So S lambda squared, so lambda is going to be some real parameter. Map T goes to lambda squared T, but I can think of it on the total space as just multiplying S3. You can think of S3 times R4 as a vector bundle, and just in the natural multiplication map on this vector bundle is the thing that I'm doing. And then, so I pull back by this diffeomorphism, and then I rescale. So unlike in the so there's ALE or fibration cases or asymptotically conical, where you're rescaling everything at the same rate. Here I'm going to do this rescaling with slightly different, in a slightly different I take slightly different scales for the metric on the fiber, which I'm going to think about the metric on the fiber as being the estimates. Let's say the fibers be the S3 that lives in the fiber is going to be this copy of S3 that lives in the diagonal of SU2 times SU2. So that's this piece on the left. And then the S3 that lives in the base is going to be this anti-diagonal copy of S3, the EI minus EI prime. Right, and I pull back the metric that my G2 metric by this rescape, by this diffeomorphism. And actually what I get is a metric of the following form, so up to scale lambda. It looks like the same on the fiber, but on the base I'm rescaling down. Sorry, I'm scaling up. I'm eventually going to take this lambda going to 0. Right. So if I actually take lambda to be my overall scale and do this rescaling, then I'm actually getting functions which converge on compact subsets of S3 times R4. And right, these BI are converging to constant, and these A1 and A3 are converging to explicit functions of R, where I'm taking R to be some parameterization of T, which I'm giving it down here. So what does that mean in terms of the geometry? The pullback metric, as I take this R0 going to 0, is giving me the Taub-NUT metric on the fiber, R4, and a scaling of the round metric on S3 on the base, on this base S3. Actually, if you do the computation, you look at the ODEs, what happens when you do this rescaling, you're actually getting an ODE for the base, which turns out for this family is satisfied at first order. So actually everything just sets to a constant. I suspect these equations, more general ODEs, are describing something about lifting your Taub-NUT metric, like different ways to lift your Taub-NUT metric, but for our purposes, it's enough to, I mean, the fact that it's just constant is a blessing, because you don't have to worry about this this lift. It's basically kind of trivial. Right. So we're seeing the Taub-NUT metric appearing on the fiber. So this is what I mean by an ALF fibration, by the way. This limit where my metric looks like a fibration of an ALF metric along a three-dimensional base. But I mean, this metric, I mean, if you look at this metric, it's no longer G2 if I do the rescaling, right? If I scale everything now, I'm not necessarily in the G2 world. But I still see this Taub-NUT metric appearing at the end. So what does that mean? So I think about solving the instanton equation on Taub-NUT. I actually get some ODE, and the picture is exactly the same as heuristically. It's exactly the same as the picture I put on the slide before, where you can basically deform for some asymptotic mass. In fact, in this case, the monopole mass, what I call the monopole mass, is exactly the monopole mass for a monopole on R3. So because this thing is a circle fibration over R3 now, Taub-NUT, is the honest BPS monopole equation, like not Calabi-Yau monopole or anything. It's just the mass. For some asymptotic monopole mass greater than a constant, in this case 1, I can deform the abelian solutions and that are generated by this S1 action on Taub-NUT, this killing vector field. And as I move far away, there's some critical, from these, as I deform further and further, there's some critical solution where I'm getting a different behavior, and then these solutions fail to be complete for all time. Actually, on Taub-NUT, the critical behavior is a bit different. You're getting actually the flat connection. I mean, all the connections in the left in the B7 case are flat as well, but I'm actually getting honest flat connection when the thing that my solution converges to is actually a flat connection. I don't have any mass at all, basically. Right. So, but what does that mean in terms of my initial conditions that I wrote down before for my solutions to my B7 G2 instanton equation? So it's the following. If I rescale my connection, so remember, if I pulling back by rescaling is just multiplying. When I take my function f1, f2, I'm just thinking about lambda squared times, I'm just sending r to lambda squared times r. So if I do that, if I pull back by the scaling, then I can take a limit that gives me a 2-parameter family of solutions of instantons on Taub-NUT, which is fibered over S3. And that's a 2-parameter family because I'm thinking of my initial conditions. So if I choose my initial conditions such that this F1 and F3 bar times R0 is fixed, R0 to power 4 is fixed, then as I take this limit, I actually get a solution to the Taub-NUT instanton equation fibered over S3 with initial conditions this constant. Right, so if I look again at the picture here, what that's telling me is that if I fix some point in this region of complete solutions, and I can move basically this diagonally, if I fix this point, I actually can get a complete solution as I move, as I change the overall scale and I move in this diagonal direction. So that tells you something, you know, about what's happening as you move. F3 is going to infinity, and F1 is going to infinity as well, I guess. So you're actually seeing, what you're seeing is instantons on these Taub-NUT fibers. So said another way, you can think about this scenario as what I'm doing is, in a suitable adiabatic limit, I'm taking a lift of my my instantons on Taub-NUT, on R4, and lifting them to the total space of S3 times R4 to get a G2, to get an instanton for a metric which is not, doesn't have holonomy G2 anymore, but if I, you know, as I move away from this limit, there is a metric in moving away from this limit, which is holonomy G2. So I'm thinking about it in this limit as lifting instantons from Taub-NUT. And in fact, this is quite suggestive, because if I'm thinking about moving outside of the invariant world, because the moduli space of instantons on Taub-NUT is in fact a hyperkähler manifold. This is proved by Cherkis and his collaborators using something called the Bow construction. But in particular, it's a 4-dimensional. It has to be at least 4-dimensional. So since you're only getting 1-dimensional things happening in this moduli space, it suggests that the invariant ones that we found, so this SU2 squared invariant ansatz, So, I mean, there's not always a reason to suspect that that they are unique, but often in these invariant, ODE problems, you actually get they have no deformations. So your invariant setting is precisely your ODEs are precisely all the solutions to your PDEs, but there should be some four-dimensional. There should be a lift of all these other ones. So this hyperkähler manifold to your space of instantons on your G2 manifolds given by your B7 family. But that is a much more complicated project, and we just leave it as a suggestion for something to prove. Okay, so that is basically everything I wanted to talk about. So just a summary of what we've spoken about today. If there's no questions, we parameterize solutions to some ODE system in two variables. We gave a geometric explanation of this set of parameters by deforming abelian instantons on, I should say on the G2 on B7 family. So by deforming abelian instantons and this monopole, these monopoles on the conifold. We then understood the limiting behavior of this parameterized solution set using two geometric limits, both the AC limit and also thinking about this adiabatic limit as an ALF vibration. And that led us to have some suggestions for how to go beyond the invariant setting, that is hyperkähler, these hyperkähler modular spaces of instantons on Taub-NUT. So yeah, we have come very far, and it's a nice, it's a nice example. You can see a lot of behavior that's happening in the modular space of instantons very explicitly. And I guess the important thing is it's mostly fully worked out. So thank you very much for listening, and please, if you have any questions, please ask them. Well, thank you.
Thank you very much, Jacob. So let's open some space for questions. Anybody wants to ask a question to our speaker?
Perhaps Jacob can explain what are future problems that could be addressed with a similar dimensional reduction. What things does he have in mind just now? The method of dimensional reduction for construction of instantons is of interest to several people. So perhaps you can motivate similar problems, perhaps not with holonomy G2, but torsion-free G2, but similar geometries or the things you have in mind right now?
So in terms of which dimensional reduction do you mean? Like a thing about instantons on the monopoles on the conifold, or these ALF vibrations? So both have, there's two things. One is understanding whether given a G2 instanton, a Calabi-Yau instanton on an asymptotically conical Calabi-Yau, can I always, and I lift it to the total space of this ALC manifold. Now it's not going to be a G2 instanton, but it's going to be almost a G2 instanton with better and better approximation as I go up to infinity. Can I deform my solution by some constant so that I actually get a bona fide G2 instanton from my Calabi-Yau instanton, written as a lift. You might ask why not monopole, which you also could do, but typically in these ALC B7, these ALC G2 manifolds, you actually, the existence of monopoles is obstructed. So just doing it with instantons would, you have more chances of having examples, and yeah, it can be done. Well, yeah, it can be done on more manifolds. I don't know of an example where you don't have this obstruction. I think you would need to lift it as you'd need to also include effects that basically come from singular monopoles. And the thing about the ALF vibrations, one very good question, one very natural question would be, can I deform my G2 instantons on my B7 in this some suitable moduli space? Do I get indeed four-dimensional or a multiple of four-dimensional moduli spaces or deformations? And do all of those come from, if I take the adiabatic limit, do all of those pass the adiabatic limit as just deformations of the Taub-NUT or the whatever ALF metric you're considering in the ALF vibration? That would be a great goal to know. Like, can you actually do this lift? I mean, if you can go the other way, it would be even better. But just one natural question is that even possible? Like, I might even get more things. So like going the other way are all generated by these definitions.
Jakob, I'm not an expert in the area, but could you explain to me if this class of manifolds of asymptotically locally conical, where do they come from? Like, where is the interest in? Where does the interest in this type of manifold come from? Is it a natural occurrence in some mathematical physics problem?
So there's the ALF manifolds, which are in the four-dimensional case. They occur in lots of physics problems. I mean, it's the somehow. I mean, this was why Cherkis was studying them as models for some string models, which I don't claim to understand. But also they're one of the best understood. So there's the second most understood gravitational instantons, so Ricci-flat, non-compact Ricci-flat manifolds. Because you have something called the Gibbons-Hawking ansatz, which is basically the metric is determined by a harmonic function on R3. So you can say a lot about, and like people understand harmonic functions very well. So you can say a lot about these metrics using this ansatz. And there's infinitely many of these types of metric. The interest in higher dimensions, or for at least ALC, so moving beyond the setting which a lot of people know, which is the asymptotically conical. Part of that is because you can construct, I think, most constructions of G2 manifolds, non-compact G2 manifolds, most in the sense of like you can get arbitrarily high dimensional families, etc. There's like infinitely many examples are these ALC constructions by Foscolo, Haskins-Nordstrom. So like they're a good testing ground for understanding what happens to G2 instantons and non-compact spaces if you go away from the setting where you're, the G2, the compact setting, or the asymptotically conical setting, because there's many examples. Did that answer your question? Sorry.
Oh yeah, definitely. Yes. Thank you. Yes. I also wanted to say that we're relatively close. I'm in Sao Paulo. We're reactivating our weekly differential geometry seminar. So if you would like to come and visit us sometimes, let us know.
Yeah,
and you can meet the group and give a talk, and we can get together sometimes. I guess you're going to be here for a few years, I guess.
Yeah, I think so. That's the length of the thing.
Sure. We're very close to Campinas, so I guess you'll meet some people of São Paulo group next week. But in case
as per your suggestion, Paulo, maybe we can put Jakob up for a talk in the second semester when we visit São Paulo. This could be an idea, yeah?
agreed.
Okay.
Okay.
All right.
Yeah, and if anyone else wants to invite me to their seminar, I'm very happy to give talks. And yeah, like I said, interact more with South American geometry.
Perfect. Would anybody like to ask another question to Jakob? If not, then we can thank again for Jakob.